Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis through a plate type of heat exchanger using ANSYS Fluent fault-tolerant meshing. This is the model. From top right side we will provide hot water. This is the entry of hot water and this is the exit of hot water. Similarly downside it is the entry of cold water and this is the exit of cold water. To understand the geometry in a better way, let us cut this geometry from different planes. Let us understand this geometry from this sectional view. When we are providing hot water from the top side, while moving in the forward direction, it is having some kind of space in the left hand side, which is shown this side. This is the space. While moving forward direction, hot water is finding some kind of space in the left hand side, and the left hand side is completely closed. So it is not having any kind of way to move out. Finally, it is coming out from this downside, right? So I'll repeat this one again. We are providing hot water from this top side, top entries, and it is moving in the forward direction. By the same time, it is having some kind of space in the left hand side, which is shown by this fishbone type of structures, and it is moving along this fish type of structures path, and at the left hand side it is not having any way to move out. It is coming down this way and finally it is coming out from this bottom side exit, right? Exactly same thing is happening from this one. When cold water is passing from this side, while passing through this bottom entry, it is being heated by hot water from the right hand side. Actually there is no direct contact between these two types of water. It is not actually being mixed. It is being heated up by convection, because we are having separate zones for this cold water and hot water. Cold water from left hand side is being heated by way of convection, and as it is being heated, so it has a tendency to go up, and finally through this bone type of structures it is going up, and finally it is coming from this top exit. So what we have done is we have created some kind of spaces alternately cold and hot regions, and from hot regions it will be conducted by way of convection. I'll repeat this one again. From top entry we are providing hot water, and while it is moving in the forward direction, by the same time it is having some kind of space in the left hand side, which is indicated by bone type of structures. So hot water will be following both directions. It will move in the forward direction, by the same time it will move in the left hand side following these bone type of structures, and as it is closed from right hand side, it will not have any kind of way to move out. Finally it will come down from this bottom structure, bottom opening. Exactly same way, alternately we have created some kind of spaces for the left hand side. Left hand side we are providing cold water from downside, as it is moving in the forward direction. At the same time it will be moving right hand side through this bone type of structures, and right hand side it will be completely closed. One thing is clear, that there is no direct mixing of these two types of fluids. We have created two different types of layers, and through these two different types of layers convection will be occurring, and by the way of convection cold water will be heated up and it will move upward direction following these bone type of structures, and as in the right hand side it is not having any kind of way to move out, it will move up and finally it will come down from this top exit. For starting this CFD analysis, we need to save this model with FM database or with the extension of FMD. We have already saved this one, so let us close it and let us start ANSYS Fluent Launcher. Let us start ANSYS Fluent Launcher from here. First of all, we need to open fault-tolerant meshing, and then we need to import that CAD geometry. Let us import the geometry from here. With the custom settings on, let us load that model. We need to drag that CAD model into meshing model. We need to create meshing object for each part. We have imported all the parts separately into meshing model. You can see here. Next to that, we need to identify what type of analysis it is. It is an internal analysis. Before going to details of this analysis, let us understand this geometry in a better way again. So what we'll do is we can have different clipping planes and see the model. Let us cut it from different planes and see again. So the thing is, when hot water is flowing from this top inlet, it will move in the forward direction. By the same time, it is having some space in this left hand side, and hot water will move in both directions. It will move in the forward direction. By the same time, it will move left hand side, and left hand side we are having these bone type of structures. Through these bone type of structures, it will move, and finally it is not having any kind of way to move in the left hand side. It will pass through these paths, and finally it will come down in this side, and from this down exit it will move out. Next plate we are having alternate different type of arrangement. Let us move on to the next plate. By clipping section we can move it to the next plate. You see, in the next plate what is happening again, cold water will be passing from this bottom entry, and by the same time it will move in the forward direction, and right side it is having some kind of this bone type of structure is there. Following this bone type of structure, it will move in the right hand side also, and right hand side again it is closed, right? So there is no direct mixing of hot and cold fluid here itself. Cold water will be moving from bottom entry, and it will move in the forward direction. By the same time it will move in the right hand side following this bone type of structures. And previous plate, it is already heated, so this is the plate backward to the first one, and it will move in the forward direction. By the same time it will move in the right hand side following these bone type of structures. It is completely stopped at the right hand side, so having no way to move out, it will follow these bone type of paths, and finally it will come out from this top exit. Okay, now in this step we have to identify what type of analysis it is. It is an internal analysis, so with internal flow analysis checked in, we can move on with the default other settings and describe the geometry. In CFD analysis, we know that closed volume should be created. That means the different inlets or exits should be closed with different types of caps. Here in this case, we are having 4 different entries, 2 inlets and 2 exits that to be capped. Let us select first hot water inlet, and that to be capped, and zone type will be velocity inlet, and we are renaming this one as cap 1. Let us create cap for hot water inlet. You can see cap is produced at the hot water inlet. Next to that, we need to create cap at the cold water inlet, and again zone type will be velocity inlet, and we can rename this one as cap 2. Let us create cap for cold water inlet. You can see cap 2 is also produced. Next to that, we need to create cap for the hot water exit, and in this case zone type will be pressure outlet as it is the exit, and we are renaming this one as cap 3. Let us create cap for the exit of hot water. It is done. Finally, we need to create cap for the exit of cold water, and again zone type will be pressure outlet as it is the exit, and finally we can rename this one as cap 4. Let us create cap for the exit of cold water. All the caps are produced. Now it is a closed geometry. We can move into the next step, that is identifying regions. In this case, we have to define the fluid domains. We are having 2 different fluid domains, hot fluid domain and cold fluid domain, that to be identified with different methods. Here we are having different methods of centroid of objects or numerical inputs or offset methods. We will use here offset methods. First of all, we need to identify hot fluid domain, and hot fluid domain is indicated at cap 1, because from cap 1 only we need to provide hot water, right? You can see at the inlet of hot water, one diamond shaped object has come. We need to push that diamond inside to indicate the location of hot fluid domain, and that diamond can be moved inside by offset of XYZ values. In this case, it can be moved in the negative direction of Z, right? You can see here at the bottom right corner, Z direction is indicating the offset movement of this diamond. So it should be moved in the negative direction of Z. Let us provide Z equal to minus 30. And see, the diamond has moved inside to indicate the hot fluid domain. To see the location of diamond in a better way, we can have the clipping pins from here. You can see it better way from YZ plane. This is the location of a diamond. It is indicating the hot fluid domain. Let us rotate this one a little bit. Right, this is the hot fluid domain. It has gone inside. You can check it from here. Right, you can push it more if you want to be confirmed about the location of hot fluid domain. You can push it more. Let us move this one to minus 50. It will show it has moved inside, and this is indicating the location of hot fluid domain. Right, we can identify this one as hot fluid domain. We can rename this one as hot fluid domain. Let us identify this region. Hot fluid domain is identified. Next to that, we need to identify cold fluid domain, and it can be identified from the location of cap 2, because from cap 2 we provided cold water. You can see one diamond is there, so that diamond has to move inside to indicate the location of cold water, and that can be done using offset methods. We need to offset the value of Z. Right, you can see here the Z should be moved in the negative direction to indicate the location of cold water. The diamond should be moved in the negative direction of Z. Let us provide Z equal to minus 50. Now the diamond has moved inside. We can check it from clipping pins. You can cut it and see the actual location of Z. See, the Z location is showing here. That means it is indicating cold water domain or cold fluid domain. We can rename this one as cold fluid domain. Let us identify this region. So we have identified two different domains of hot fluid and cold fluid. Excluding that one, we have to identify another domain known as void domain, which is required to restrict the flow movement from inside to outside, and region type it will be void domain. For indicating the void domain, let us select the whole object, and the diamond should be moved outside this geometry. Right, let us see the location of diamond here with clipping pins. Diamond is actually inside. The diamond should be moved away from this plane. So what can you do is, we can move the diamond by using offset method. You can move the object out in the y direction up. Let us provide y equal to 300 millimeter. Again, we can move it a little bit up to indicate the location of diamond outside this domain. Right, it is okay, fine. See, the diamond is outside this plate type heat exchanger, which is indicating void domain. Right, let us identify this one as void region. So what we have done is, we have created three different domains: hot fluid domain, cold fluid domain, and also void domain. Excluding that one, by default one solid domain will be created, and as it is a heat transfer analysis, so we need to consider that solid domain also. Solid domain will be indicating the solid materials. Next to that, we need to see the leakage threshold options. Let us consider we are having some leakage. We can identify that one also. If it is having any kind of leakage, that will be rectified here itself. Let us consider cold fluid region with the leakage, and maximum size of leakage we are considering as 6 millimeter. If any leakage is here, that will be closed. We are considering this one as leakage 1. In cold fluid region, let us define leakage threshold here. It is done. Next to that, we need to identify any other leakage at the hot fluid region also. We can select hot fluid region, and with the maximum leakage size of 6, we can identify define leakage threshold. So if any leakage is there, that will be closed. Next to that, we need to update regions, and you can see here we have got different domains as cold fluid region and hot fluid region. By the same time, we got some kind of void domain also. You can see we have created 3 different domains. Excluding that one solid domain has been created. It is showing as void, that to be converted as solid domain, as it is a heat transfer analysis. So we need to consider this solid domain also, and we can mesh all the different parts separately with different types of meshing criteria. This hot and cold fluid domain will be considering polyhexagonal meshing, and the solid domain will consider tetragonal mesh, and the void domain we need not consider any kind of meshing. We are considering 3 different types of zones, and that is solid zone, hot fluid region, and also cold fluid region. Both the fluid regions we are considering polyhexagonal meshing, and for solid object we are considering tetragonal mesh. With that one, we can update these regions, and with the default settings, we'll move on to the mesh control options. Next to that, we need to generate surface mesh with the mesh target skewness to be 0.8. Let us generate surface mesh here. We can see here surface meshing is complete, and overall summary is saying that skewed cells more than 0.8 is 26, and average skewness is 0.033, and maximum skewness is 0.98, and face count is 0.97 million. And we can see here different boundary types have been created. We have got 2 velocity inlets and 2 pressure outlets. Velocity inlet will be providing the inlet of hot and cold fluids, and pressure outlets are indicating the exits of hot and cold fluid. Excluding that, we are having different types of walls. Through all these walls, heat will be transferred by convection, right? Next to that, we need to update these boundaries, and we can reduce the numbers of boundary layers to 2, and let us update these boundary layers. Finally, we need to generate volume mesh, and in this case we are considering quality improvement limit to be 0.04. So let us generate volume mesh. We can see here volume mesh is generated, and overall summary is telling that quality less than 0.1 is 18, and quality less than 0.04 is 1. Minimum quality is 0.038, and cell count is 5 million. And you can see the quality of mesh from here. It is showing that minimum orthogonal quality is 3.7 into 10 to the minus 2, and maximum aspect ratio is 6.36 into 10 to the 3. So with this one, we'll switch on to solution mode. While initiating solution mode, first of all, we need to select units, and we'll consider length as millimeter, and temperature will be in degrees centigrade. Let us close it. It is a steady state analysis, and in this case gravity will be involved. The direction of gravity is indicated by this green arrow. It will be minus 9.81 meter per second square in the direction of y. Next to that, we need to select models. As it is a heat transfer analysis, so energy equation should be on. And it will be K-epsilon to turbulent model, realizable and scalable wall functions. Next to that, we need to select materials. Fluid is water. That means water from different temperatures will be provided from different entries. So we'll consider water as the main fluid, and we can select water from fluid database. Let us select water from here, water liquid, copy, and the solid we'll consider as copper. Let's select solid from here, and the plates are made up of copper, copy, close. We have selected fluid as water and solid as copper. Next to that, we need to see our cell zone conditions. That means we need to define our fluid and solid domains. You can see here we are having two different domains, cold fluid and hot fluid. In both cases, we have to provide water. Cold fluid domain, it will be filled up with water at lower temperature, and hot fluid domain will be having water at higher temperature, but actual temperature will be provided during applications of boundary conditions, right? Now, cold fluid domain, it will be filled up with water. Let us apply and close. Next, hot fluid region, again it should be filled up with water at higher temperature. So material for hot fluid region is water liquid. Apply and close. Now we'll provide material, that is for solid. We can provide different materials for different types of gaskets or like different plates, but for ease in simulation, we'll consider all this material as made up of copper, right? Let us select one. It is made up of copper. Apply, close. Now the same fluid domain can be defined for the remaining cases also. Let us copy this. And the same property to be transferred to the remaining solids. Let us select one by one. That means all the solids will be made up of copper. In this case, if you want, we can provide different materials as per your requirement. Let us copy. So same materials have been provided for all the solids. Let us close it. Next to that, we need to see our boundary conditions. That is actual fluid at actual temperatures to be provided at these locations. Let us see inlet. It is having two inlets, cap 1 and cap 2. Cap 1 is the inlet of hot water and cap 2 is the inlet of cold water, right? Let us select cap 1. From cap 1, we will provide hot water at a very low velocity. Let us consider velocity of hot water to be 0.001 meter per second, and temperature it will be 100 degrees centigrade. Apply and close. And for the cold water, velocity will be 0.001 meter per second and temperature will be only 10 degrees centigrade. Apply and close. Both the inlet boundary conditions have been defined. Next to that, we need to see the outlet boundary conditions. That means at the exit of hot water and exit of cold water, it will be zero gauge pressure. Cap 3 is the exit of hot water. This one will be having zero gauge pressure. Apply and close. Exactly the same way, cap 4, that is exit of cold water, it will be also having same boundary condition. It will be having zero gauge pressure. Apply and close. Next to that, very important thing is walls. In this case, all the walls will transfer heat by convection. So we have to provide convective heat transfer coefficient at a specific rate. Let us select any one. And this wall is made up of copper, and it will transfer it through convection. We are considering convective heat transfer coefficient as 20 watt per meter square degree Kelvin at a temperature of 30 degrees centigrade. And let us consider wall thickness to be 0.01 millimeter. Let us apply and close. Now the same boundary condition to be applied for the remaining walls. Let us copy this one, and same boundary condition to be applied for the remaining walls. Let us copy all these things one by one. Copy. Okay, that means exactly same boundary condition is applied to the remaining walls. Let us close it. That means all the boundary conditions have been applied properly. Next to that, we need to select solution methods. It will be coupled method. For special discretization, we are considering Green-Gauss node-based method, and pressure will be second order. Momentum is second order upwind. Turbulent kinetic energy is second order upwind, and turbulent dissipation rate also second order upwind. Next to that, we need to start initialization, and we'll start standard initialization, and it will be started from all zones. Let us initialize. Initialization is done. Finally, you need to run calculations, and we are considering 100 numbers of iterations. Let us calculate. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Right? Calculation is complete. Now we can see our results, and that can be viewed from here. And initially, we want to see results from reports, surface integrals, and report type will be facet average. We have to see temperature distribution at the exits of plate type heat exchanger. From boundary conditions, we know that we have provided a temperature of 100 degrees centigrade at the hot water inlet, and at the cold water inlet we have provided a temperature of 10 degrees centigrade. Hot water indicating cap 1 and cap 2 indicating cold water. And from this one we will get the temperature at the exits like cap 3 and cap 4. Cap 3 is the temperature at hot water exit, and cap 4 is the temperature at the cold water exit. We have to find out all these temperatures, and excluding that we can find something else, like we can find temperature at hot fluid domain and cold fluid domain. This will be the average temperature. Right, let us compute these things. Cap 1 is the inlet of hot water. It is showing temperature of 100 degrees centigrade, and cap 2 is the inlet of cold water, that is showing 10 degrees centigrade. And we are having cap 3, that is the temperature at the exit of hot water. It is 54 degrees centigrade. That means hot water has lost a huge amount of heat. Its temperature has gone down from 100 degrees centigrade to 54 degrees centigrade. Similarly, temperature of cold water has risen from 10 degrees centigrade to 22.28 degrees centigrade, and cold fluid region average temperature is 28.434 degrees centigrade, and net temperature is 30 degrees centigrade. Right, so this is the main thing we want to see. Let us see velocity also from here. Instead of temperature, we want to see velocity distribution through the same locations. Let us compute. We can see here velocity at inlet and exit of hot and cold water. In both cases, is almost same, very little difference is there, right? Let us close it. Excluding this one, when you see different conditions of temperature, pressure and velocity distribution through different locations, right? We have created two planes, and when you see temperature, pressure and velocity distribution through these different planes, right? First of all, you see through plane number 74. This is showing temperature distribution through right plane, and it is showing that at the surfaces of plate type heat exchanger we are having alternate cold and hot regions, and temperature of this one is indicating clearly. First one is hot region, second one is cold region. Alternately, it is having hot and cold region. Next one, we see temperature distribution through plane number 75. Let us display. This is temperature distribution through a specific plate. As from the top side, we are providing hot water, and while hot water is passing in the forward direction, it is having some kind of space in the left hand side, and this hot water is spread throughout the left hand side, and finally it is coming downside, and the temperature of this one is indicating that downside temperature is in the range of 46 to 55 degrees centigrade, and top side temperature is in the range of 90 to 100 degrees centigrade, right? This is regarding one plane. We have seen that in the plate type heat exchanger we are having alternate hot and cold region. So what we'll do is we'll make different planes along this one. Along front side we'll make different planes and see the distribution of temperature and pressure, right? So let us make some other planes also. Let us create several numbers of XY planes. Let us create 5 numbers of planes, and in between them we are having some distance of, let us provide 100 millimeter. We have created 6 numbers of plane, and through these planes we want to see temperature, pressure and velocity distribution for this plate type heat exchanger, because in plate type of heat exchanger we are having alternate regions of hot and cold, right? So contours, new, want to see temperature distribution through different planes like what I've told right now, plane 76, 77, and all these planes we'll consider. Let us display. It is showing through different planes. Alternately, we are having hot and cold region. From this one, it is clearly understood that initially we are providing hot water from this top side, which is indicated by red color. It is clearly visible that hot water, while flowing in the forward direction, it is having some kind of space in the left hand side, and following some tracks, it is following the path in the left hand side, and finally it is coming down. You see temperature at the top side is 100 degrees centigrade, and downside it is in the range of 46 to 60 degrees centigrade. You can see here indicated by light yellowish green color. Okay, let us rotate this one and see differently. So we are having different regions of cold and hot, right? This one hot region, this is cold, again hot. Alternately we are having hot and cold regions, right? Next to that, we want to see pressure distribution through these different planes again. Instead of temperature, we will see pressure distribution. Let us display along these specific planes. It's showing the pressure within these different planes. We are not having that much of difference. All planes are having almost similar type of pressure. Let us see velocity. Velocity also we are not having that much of variation. Through all the different planes we are having almost similar type of velocity, right? Next one, what we'll do is we have to see the dynamics of flow particles through this plate type heat exchanger that can be viewed from path lines. From particle variables, let us consider temperature, and when you see dynamics of flow particles through these different planes, through these specific planes, it is showing the path of hot and cold water regions, right? You can see here, this is the passage of hot water and this is the passage of cold water down. It will be better to see this flow pattern in the form of an animation. So let us have a pulse of this one. You want to see the dynamics of flow particles in the form of an animation, right? Let us see that. This is all about our today's analysis. It was a very simple analysis of a plate type of heat exchanger. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.